So I'm Estefania Recayte. I'm with DLR, so the German Aerospace Center. I work for the Institute of Communication and Navigation. So the title of my presentation should be something like mutual collaboration between satellite networks. So let me give you some context. So already with 5G, we have faced many challenges. Like we wanted to transmit at high data rates. We wanted to have more reliable communications. So think about that. Today it's possible to have autonomous cars, to have remote healthcare or smart city. And with 6G, we expect that these challenges are more evident, and we want to, or we think that the target will be more ambitious. So for example, we want to increase orders of magnitude, what is the data transmission rate. We want to have worldwide coverage. And one of the main issues, both in 5G and 6G, in terrestrial and in satellite network, is the spectrum availability. So we know that the resources are finite, so the spectrum is limited, and we need to find more or alternative ways and more smart ways to use the spectrum. So one of the solutions for achieve these high data rates or high capacity is to use another part of the spectrum. This is a key solution, and here I'm citing some papers because it's made me a little smile, because the terrestrial community thinks that they can use satellite bandwidth without maybe disturbing too much the satellite community, but the satellite community has not any benefit if the terrestrial use our bandwidth. On the other hand, if we want worldwide coverage and we want service availability, obliquity, and continuity, the solution here is to use the satellite component. So let me focus a little bit in the different parts of the spectrum solution. So the candidate bands to use are the millimeter wave. We have here this about these days. So the millimeter wave is the band between 30 gigahertz and 300 gigahertz. And today, transmitting in this part of the spectrum is possible for terrestrial because we have made, or they have made in research, many advances in antenna arrays. They have adaptive beamforming, very narrow beamforming, and signal processing. So the idea here is to place a small base station, each one what is called G0B in 5G, and each one is placed very close to each other. So the path between the user and the small base station is very short, just in the order of, or at most, 100 meters. From the other side, if we want to use the satellite component, also here, today we have heard that from Release 17, the satellite is part of the ecosystem. So the satellite has been standardized, and we can think that it's realistic to use the satellite for saving services. And the fact is that millimeter waves have been already used in satellite, so we have experience on it, have been used for fixed satellite services, for inter-satellite links, for transmission from the ground to the satellite. However, there is a main limitation of using millimeter waves in satellites, and this is the attenuation of the atmosphere. When the signal crosses the atmosphere, we have attenuation, and the worst thing that we have is the rain. The rain can make the service unavailable, and yes, in the worst cases, we can have outages. So let me take just 2 words about the rain. The rain can significantly be from 10 gigahertz because the wavelength, so our lambda, is in the size of millimeters, so it's comparable to the drop size. And when the signal crosses the drop, a drop of rain, the drop attenuates, make scattering, scintillation, and refraction of the signal, and can, of course, destroy the signal. So the attenuation depends on these factors, so from the elevation angle of the satellite, on the frequency that we are operating, on the intensity of the rain, on the, and also on the slant path length, that is the length that the Siena had to cross through the rain. So for example, here, I plotted in the x-axis the frequency, and the y-axis the rain attenuation in dB per kilometer. And we see if we increase the frequency, the rain attenuation is larger, but also, okay, here the different colors are different intensity of rain, measured in millimeter per hours. So for example, if we have a satellite beam that is covering the UK, and if we are working at a frequency of 30 gigahertz, the length of the slant path can be between 2.7 and 3.3 kilometers. So if we are having light rain, the attenuation in total can be up to 165 decibels. But if we are having heavy rain, we can have up to 15 dB almost of attenuation of the rain. So I have found in literature many solutions in order to compensate this rain fade. For example, we can have site diversity. So this means that we can place ground stations in different parts of the world, but this will cost in terms of infrastructure, and we don't know if we really want to invest in this. We can increase also what is the power margin. So in our link budget, we can increase this margin, but this means also more power consumption, more interference, and maybe the problem can be not solved, because if we have more higher rain, also if the margin is not enough, we can also have outages. Another solution can be using more robust coding and modulation, but this means also to increase the complexity and also to increase the latency, and we don't have advantages in this. So the solution that we are proposing here today, we can refer to the following scenario in which we have a satellite that is illuminating a part, a GEO or LEO satellite, and we have users, satellite users, and we have as well as DG terrestrial network with GNB small cells and a macro base station. So we have users from the terrestrial, and let's assume that there is a rain that is affecting one of the cells. So such that the communication between the satellite and our satellite user is not possible. So the solution that we want to propose is to use the terrestrial infrastructure in order to relay the signal from the satellite. So this will help the satellite to have a connection. And in compensation, so the collaboration here is that we allow the small cell which is affected by rain to use the satellite frequencies. And here there is one advantage, is that we can be sure that if you use the frequencies when it is raining, I will not cause interference to the others, because the rain will attenuate also the interference that I am using in the small cell. So I thought about defining two different parameters. One can be alpha, that depends on the frequency f, and this is the minimum rain intensity that I need, or that I know that the connection between the satellite and the user is not possible. I can define another parameter that is beta, that depends on the frequency, and this is the minimum rain intensity that I know that if the frequency is used in the cell, I will not cause interference outside because of the rain. And the collaboration will take place if, for example, if we are considering the return link, the user can estimate what is the rain intensity. And if this rain is smaller than the alpha parameter, the communication will continue because I know that I am able to communicate. If this rain is larger than the parameter that we define, so now the communication stops, and then the satellite or the user will use the terrestrial network in order to communicate with the satellite. And the small cell will be able to use the satellite frequencies. So in this case, the satellite, we don't experience an extra bandwidth loss. The routing in the terrestrial can be done with already that infrastructure that already exists, maybe with high capacity optical fibers or radio frequency links. And okay, this I already tell you, each time that the intensity of rain is larger than the parameter beta that is the parameter for the interference, we will allow the terrestrial to use the satellite frequencies. So I identify some requirements. One can be that the small base stations, so the G0B, needs to have communication with the satellite. But today, this morning, in the presentation that we hear, he told that it's already possible, that the community is already thinking to implement this. Also, we need that the satellite users are able to communicate with the terrestrial network, and we think that also this could be possible. I identify some research direction that we can do in order to implement this idea, maybe to study interference characterization, routing, frequency allocation, and rate intensity estimation. So I think I'm on time. So I go to the conclusions. So the challenge here was to have a reliable communication between the satellite and user when it is raining. And what we're proposing is to a mutual collaboration in order that terrestrials use satellite frequency when it's raining, and the terrestrial helps to the satellite user in order to route the signal in their infrastructure. This is all, and thank you for your attention.